Okay, property 9. In this video, we're going to focus on property 9 and its consequence. It talks about finding the determinant of the product of two matrices. And it says that to find the determinant of the product AB, you could either multiply AB and then find the determinant, or you could find the determinant individually and then multiply the numbers to get the answer. There are a number of ways to prove this. The proof I'm going to outline here is a pretty clever one, and I first read it in Gilbert Strang's book from MIT. He defines a function of A called determinant, and the way he defines it, he says, okay, assume there is this function determinant, and the way you find the determinant of this matrix A is if you multiply it with B and find the determinant and then divide by the determinant of B. And what he tries to do is say that this determinant function we're defining is essentially the determinant function that has the defining properties. It's the same determinant function, it's not some new number. Okay? So we start by just naming the product AB. We name it C, and we're just writing here the entries of A in the standard way and the entries of C in the standard way. We first have to establish that the determinant of the identity matrix is 1. Let's see if this formula establishes that. Okay? So according to that formula, this new thing, the determinant of the identity is the determinant of identity times B over the determinant of B, which is, well, identity times any matrix is that matrix itself, and so this is of course equal to 1. So that makes sense. So this property is satisfied by this new definition of determinant. The next property says interchanging two rows changes the sign of the determinant. So what we're going to do is, here's A times B equals C. Now what happens when I interchange two rows of A? When I interchange two rows of A, remember that the first row of A in A times B is responsible for the first row of the answer. And the last row of A in A times B is responsible for the answer in the third row. So if I interchange these, then what's going to happen is the same numbers just get interchanged in the answer. Nothing else changes except interchanging two rows in the left matrix in the product is just going to interchange the rows in the matrix in the answer, in the product answer. Okay? So that means that the determinant of A star, we'll call this, or maybe not, star is used for something else. Let me call A prime, which is this. Okay, the determinant of A prime is equal to the determinant of A prime B over the determinant of B. And the determinant of A prime B is right here. This is A prime B. And we know that the determinant of A prime B is basically negative this previous one, determinant of AB. But then this fraction, without the negative, is specifically what we're calling determinant of A. So as you could see, A prime comes from just interchanging two rows of A. We've proven using this formula that that property holds, that if we interchange two rows, the determinant changes sign. And therefore, property 2 is satisfied by this new formula for determinant. Finally, property 3 says that the determinant is a linear function of its rows. Okay? So here, take the A that we had before, and if we were to add x, y, z to the first row, we could break that up using linearity. And so now, when we're multiplying in the formula of AB over B, in the determinant AB over B, let's see if we can actually do this. Okay? Now, this is a little more tricky to understand, that when you add a number to a row, how does that multiplication with B affect the answer? How does that relate it to the answer? Well, turns out all that actually does is it keeps the numbers there that were there to begin with the original matrix, and it just adds x prime, y prime, and z prime. Okay? And so that allows us to actually break up the numerator into two determinants. And again here, the determinant, we're using the formula. So the determinant there comes from the determinant of AB over B. And after some algebra, what do we get? We get the determinant of the original A plus the determinant of x, y, z in the first row, so keeping the second and third row the same. This is exactly linearity. Okay? Now, I'm gonna have to go through this one more time in class. So, go through the notes again, carefully. And it's a very tricky thing to do, but the overall picture I'd like you to understand is that to say that this formula is true is equivalent to saying that this definition of the determinant follows the same defining properties that of the determinant we know, and for that reason, that formula is valid, which in turn proves that this formula works. Okay? Now this whole proof is assuming that B is invertible. Of course, if B is not invertible, then neither is AB, in which case the left side of this equation would be 0, and the right side of this equation would be 0 because the determinant of B by itself would be 0. So if B were not invertible, this formula works. So that's why the proof only focuses on if B is invertible. Perhaps more important than proving this is understanding that it works and getting a very important consequence of this. Let me talk about a very important consequence of property 9. I'll write it down here. An important consequence of property 9 is that the determinant of A times A inverse, assuming A is invertible. Assume A is invertible. Okay. Now the determinant of A times A inverse is basically the determinant of A times the determinant of A inverse. This is just by the property we just proved. But we know that A times A inverse is actually the identity, and the determinant of the identity is 1. So ultimately, what we're saying here is that the determinant of A times the determinant of A inverse is 1. Therefore, the determinant of A inverse is just the reciprocal of the determinant of A. And that's a really cool result. So if we know the determinant of A, we automatically know the determinant of A inverse.